This video will cover the synthesis and reactions of thioethers. Thioethers are the sulfur analogs of regular ethers. An alcohol contains one carbon-oxygen bond. An ether contains two carbons bonded to the oxygen. Analogously, a thiol contains an SH group, and a thioether contains two bonds from sulfur to carbon. Because sulfur and oxygen are in the same column of the periodic table, they react similarly. However, remember that sulfur is larger and less electronegative than oxygen. Therefore, it's a better nucleophile and a worse base. Typically, thioethers are synthesized using the Williamson ether synthesis. This synthesis involves the attack of the thiolate ion on a good electrophile. For example, this thiolate can attack this electrophile, kicking off the leaving group in an SN2 reaction to produce the thioether product. Remember that to produce the alkoxide ion, we needed a strong base or sodium or potassium metal. However, because the thiolate is a weaker base than the alkoxide, the thiol is a stronger acid and can therefore be more easily deprotonated. We can use sodium hydroxide to deprotonate a thiol to synthesize the thiolate for a Williamson ether synthesis. If we treat a thiol with sodium hydroxide, the hydroxide will deprotonate the thiol to produce the thiolate. We can determine that the equilibrium for this reaction lies to the right if we compare the strengths of the bases. Hydroxide is a stronger base than the thiolate ion. This is because sulfur is larger than oxygen and can better stabilize the negative charge. Therefore, it's happier with the negative charge and the weaker base. Remember that an acid-base equilibrium favors the formation of the weaker acid and base pair. Therefore, this equilibrium lies to the right, and we can use sodium hydroxide to deprotonate the thiol and synthesize the thiolate for a Williamson ether synthesis. Next, let's look at some example reactions using the thiolate nucleophile. Just like we saw in the Williamson ether synthesis of oxygen ethers, primary thiolates react very well with primary substrates to produce the thioether. If we treat this thiolate with bromoethane, it will rapidly undergo an SN2 substitution to produce the thioether product. Remember that the Williamson ether synthesis with oxygen-containing nucleophiles does not work well with secondary substrates, and of course, SN2 reactions never occur with tertiary substrates. However, because thiolates are better nucleophiles than the alkoxide ion and are less basic, they can perform an SN2 reaction with a secondary substrate. For example, if we take the same thiolate and react it with a secondary alkyl bromide, such as this one, we will see primarily the SN2 product, the thioether. Because this follows an SN2 mechanism, we will see inversion at the chiral carbon center. Next, we will consider the reactions of thioethers. Remember that ethers are not very reactive. However, sulfur is a better nucleophile than oxygen, so thioethers are in fact nucleophilic and can undergo SN2 reactions. If we take this thioether and react it with an alkyl halide, it will react in an SN2 mechanism to produce something called a sulfonium salt. For example, if we take this thioether and react it with methyl bromide, it will react in an SN2 reaction to produce this sulfonium salt. Sulfonium salts are useful synthetically as alkylating agents. In other words, they make the carbon attached to the positively charged sulfur into a very good electrophile. This is a similar effect that we see with a carbon attached to an oxygen in a carbonyl. The carbonyl makes the carbon a very good electrophile because the oxygen acts as an electron acceptor when a nucleophile attacks. A sulfonium salt reacts in a similar fashion. The carbon attached to the sulfur is a good nucleophile because the sulfur can accept the extra electrons that are donated by the carbon when it is attacked by a nucleophile. In both cases, the oxygen of the carbonyl and the sulfur of the sulfonium ion are acting as an electron acceptor, making attached carbons good nucleophiles. Now let's look at an example. Pyridine is an example of a good base, but typically a poor nucleophile. But pyridine can be alkylated using a sulfonium salt. If we react pyridine with the very good electrophile of this methyl sulfonium salt, it will react in an SN2 reaction to produce the methylated pyridine. This also produces the thioether. This type of methylating or alkylating reaction is very important to biosystems.